video of AQA P2 physics. It's electricity. So starting with electric circuits. Electric current is the rate of flow of charge. It's calculated as I, which is current, equals Q, which is charge, divided by T, which is time. Current is measured in amps. Charge is measured in coulombs, which is the symbol capital C, and time has to be put into seconds. Then moving on, potential difference is a measure of the amount of work done per coulomb of charge passing between 2 points in the circuit. It's the work done per unit charge. Potential difference measured in volts equals work done in joules divided by charge in coulombs. Make sure that you have memorized all of these circuit symbols. Any of these could be given to you and you could be asked what they are. Equally, you could be asked to draw any of them. So you need to be confident with that. You need to be able to explain how to produce a current potential difference graph, and you need to be able to draw them for various different components. So the first thing, when we're creating a circuit to put in create a current potential difference graph, as well as the components that you're measuring the current and potential difference of in the power supply, you will also need an ammeter, which goes in series, a voltmeter, which goes in parallel with the component, and a variable resistor. The variable resistor is there to change the current, so you can get a variety of different readings of current. For an ohmic conductor, drawing a current PD graph, you'll get a straight line going through the origin. That's because current and potential difference are directly proportional, and the gradient there was 1 over the resistance. So Ohm's law tells us that the current through a resistor is directly proportional to the potential difference across it, as long as the temperature is constant. The equation potential difference is current times resistance, or V equals IR, and resistance is measured in ohms. So if there's more resistance, less current can flow in our circuit. First type of circuit you need to look at is series circuits. Nice and easy. If you've got more than one resistor, then the total resistance is equal to the sum of the individual resistances. You just add them up. The current is the same through all the components. That's because the current can only go one way round, but the potential difference, or the energy, is shared between the two components, or however many components there are. In parallel circuits, the potential difference across each component is the same. That's because the current is either going to go through one branch or another branch, or the other branch. So if you've got current, that's going to split between the two branches. So for example, if we have 5 amps, it might split evenly and do 2.5 amps through either branch. But then each of those coulombs of charge that is carrying energy is going to give up all its energy to the component on that charge. So the voltage of the battery will be equal to the voltage across each of those resistors. You need to know and draw IV graphs. So the first one you need to know is the ohmic conductor, which we've already looked at. Then the next one is the first one on this slide, which is the filament lamp. Now that has this characteristic S shape. That's because what happens is when the current in the filament lamp increases, the temperature of the filament also increases. Because the temperature is increasing, it's harder for the electric current to get through, so that resistance has increased, and as a result it takes even more energy for the current to increase further. The second component that we've got here is the current potential difference graph for a diode. Now the characteristic feature of a diode is that it only allows the current to pass through in one direction. So if the current is going in the negative direction, then it is equal to 0. If it is going through in the positive direction, then there's very little resistance, so we will get a rapid increase in current. So you need to know about LEDs, LDRs, and thermistors. LEDs are light-emitting diodes. They are just diodes that give out light. LDR stands for light-dependent resistor. If the light intensity increases, the resistance is going to decrease. Equally for thermistor, if the temperature increases, the resistance decreases. And if you're asked to sketch a graph of how that looks, same shape of graph if you're looking at an LDR for light intensity. Right, AC and DC. Direct current is only flowing in one direction. Alternating current is constantly changing direction, so the electrons are vibrating backwards and forwards. In the UK main supply, that's at a frequency of 50 Hz, 50 times per second, and the maximum voltage 230 volts. You need to know about plugs and the structure of a plug. You need to know what all the wires are. You need to know what colour the insulation is on each of the wire and where they're attached in the plug. The case of the plug is made of plastic because it's a good insulator, and the pins are made of brass because that is a good conductor. The wires are made of copper because that is a good conductor as well. Also note that you have a cable clip grip to keep the cable from falling out, and you have a fuse in the plug. The purpose of the fuse is to stop the current becoming too large, so we want to pick the next current up. So if your appliance is using 2.5 amps, you'd want a 3 amp fuse. So for electrical safety, if the current ever gets too big, a fuse or a circuit breaker can be used to break the circuit. A fuse will melt or blow, don't say blows up, and the RCCB uses an electromagnet to detect differences between live and neutral wires, and that causes a switch to flick. Quicker and easier than fuses. If you've got a metal case appliance, it needs to be earthed. If it's double insulated, it has a plastic case, it doesn't need an earth wire, and the earth wire just takes the current from the appliance down to the earth. So, current, charge and power. Current going through a resistor causes it to get hot, as we discussed in the case of the filament lamp, and we can calculate the amount of power through an electrical appliance as the amount of energy divided by time. Power in watts, energy in joules, and time in seconds. Power can also be calculated as the current times the potential difference. So again, power is in watts, current needs to be in amps, and potential difference in volts. We can also calculate the energy as the potential difference times the charge. So energy again in joules, potential difference in volts, and charge in coulombs. And all of those equations are on your equation sheet. If you're a higher tier candidate, you will need to be able to rearrange them. Right, Rutherford scattering. Rutherford did an experiment where he fired alpha particles at a thin sheet of gold foil to see what would happen. The previous model had been the plum pudding model, which suggested that the atom was mostly positive charge with little electrons embedded in it. And this proved that wrong. Why? Because most of the alpha particles fired at the gold foil were undeflected, suggesting that most of the atom was actually empty space. Some were deflected by small angles, which suggested that the centre of the atom was positive, and a tiny number were deflected by very large angles, which tells us that not only was it positively charged, but the nucleus has a very dense core. So there's a dense nucleus surrounded by empty space. Okay, you need to know about fission and fusion. Fission is the splitting of a large nucleus, such as uranium-235 or plutonium-239, to form smaller nuclei. The process starts with a neutron being absorbed by the uranium or plutonium. This causes the uranium or plutonium to fission, releasing further neutrons, dorsal nuclei, and a load of energy. Those extra neutrons that are created can go on to hit other uranium nuclei, which causes a chain reaction. In order to reduce the rate of that chain reaction, we use control rods in nuclear power plants, which absorb neutrons, therefore slowing down the rate of reaction. Nuclear fusion, the joining together of two small nuclei to make a larger one, which is found naturally in stars. Stars can produce up to iron through fusion, but heavier elements can only be formed in supernova, and that's the evidence that we have that our planet was formed from the remnants of a supernova, because we've got elements heavier than iron. So what is the life cycle of a star? Well, star starts out as a large cloud of dust and gas, which we call a nebula. Gravity pulls that cloud of dust and gas together and forms a protostar. When fusion starts in the protostar, it creates a pressure outwards called radiation pressure, and when that is equal to the force of gravity pulling it inwards, we get what's called a main sequence star, which is a stable star, which is what our sun is at the moment. It's at this point that we split between large stars, larger than our sun, and smaller stars, about the same size as our sun. So for a star like our sun, it will then expand and turn into a red giant when it's run out of fuel for fusion. If it's a larger star, instead of going into a red giant, it will expand into a red supergiant. After the red giant stage, for a small star, it will turn into a white dwarf. It will lose its outer layers, contract, and form this small, very bright star called a white dwarf. And eventually, over time, that will then cool down and form a brown dwarf, because it stops giving off radiation. The red supergiant will end its life in an explosion called a supernova. And what's left after the supernova could be one of two things. If it's a smaller supernova remnant, that will turn into a neutron star, which is incredibly dense. It's entirely made up of neutrons. And if it turns into a larger remnant, it could turn into a black hole, which has gravity so strong that light cannot escape.